Hi everyone. So today we are going to be covering section 10.3 from our textbook, which talks about infinite series. Now, infinite series is going to kind of be our theme for the rest of chapter 10. So this is kind of a more in-depth overview of these infinite series, as well as a couple of the techniques that we're going to be using to actually tell whether an infinite series is going to converge or diverge. Right, so just as a recollection from section 10.1, right, recall that we have this notation with this capital sigma of from n equals 0 to infinity of an is just saying, okay, well, we're going to take the 0th term and add the first term, add the second term, so on and so forth, all the way out to infinity, where this n could possibly be something different. And we would like to know, well, whether this is going to actually go to some specific value or whether it's going to diverge. And the way that we are going to do this in this course is we are going to talk about the partial sums. So for example, in this case, we have that S sub k is going to be the sum of the first k terms. So a0 plus a1 plus all the way up to ak minus 1. And we're going to write this as the sum from n equals 0 to k minus 1 of a n. All right, so the bottom number in these sums is always going to be the lowest value we possibly accept. So in this case, it's 0. We could do 1, 2, 3, 4, anything like that is possible for this. And then the top number is going to be the largest value. So for infinite series, we have all adding up all of the terms. And for our partial sums, we're just adding up the first k terms. Okay, and we say that n equals 0 to infinity of a sub k converges to whatever this limit as k goes to infinity of s sub k is, right? So if these partial sums get closer and closer to some value, so if we add up the first trillion terms or something like that, and we're getting closer and closer to some value, this is going to be what our infinite series is going to converge to. And similarly, if our partial sums, our sequence of partial sums, diverge, then we are going to say that our infinite series is going to diverge. Okay, so the two things we will be talking about today with respect to this are going to be what are called geometric series. So this is a very common series that you will see and how to deal with these. And then we will also be talking about what are called telescoping series. Okay. So the first thing is geometric series. Okay. So geometric series is going to be anything of the form where we have k equals 0 to infinity of a times r to the k. So some examples of this. Examples are going to be k equals 0 to infinity of 3 times 1/2 to the k. Other examples, k equals 0 to infinity of 17 times 8/7 to the k, anything like this. Some non-examples. Sum from k equals 0 to infinity, 1 over, say, k, right? This doesn't really fall into this formula we have here for these geometric series, and so this is not an example of a geometric series. Geometric series will always be some constant times something raised to the kth power, right? So this is going to look like a, and then plus a times r plus a times r squared plus a times r cubed plus dot dot dot. Okay. So now would be a great time to think about it and think about what type of conjecture you might think would hold for this. So when do you think geometric series converge? When do you think they diverge? If they do converge, what value they converge to, all of this stuff. Okay. So what we need to do, right, whenever we're dealing with these infinite series is we need to talk about our partial sums. So if we have the nth partial sum, well, we know this is going to be the sum from k equals 0 to n minus 1 of a r k, which is, as we said before, just a plus a times r plus a times r squared plus all the way up to a times r to the n minus 1. Okay. Now, what's really interesting about this, right, if we were to multiply everything in this by r, it would look a lot like the sequence we have already. So this is s sub n. And if we look at r times s sub n, this is going to be a times r plus a times r squared plus a times r cubed plus, and then all the way up to a times r to the n now, because this last term gets an extra factor of r. So what we do to actually figure out a nice explicit formula for these partial sums is going to be taking these two ideas and then subtracting them from each other. So we take s sub n and we subtract r times s sub n, and we're going to be left with just a few different terms. So in particular, s sub n minus r s sub n is going to be equal to a minus a r to the n. And again, the reason we're doing this, right, we are trying to come up with some type of formula for these partial sums so that we can use our sequences techniques on the partial sums in order to determine what the infinite series is actually going to converge to. So dividing both sides by 1 minus r, we get that Sn is a 1 minus Rn over 1 minus r. Okay. Well, this almost makes sense. This does not make sense in the case, however, where r equals 1, because then in that case we are dividing by 0, which is something we never want to do as mathematicians. So we'll deal with the r equals 1 case later. Let's just say for this instance that r is not going to be equal to 1. Okay. So we have this nice formula for these partial sums, and so we know that the sum k equals 0 to infinity of a r to the k is going to be equal to the limit as n approaches infinity of these partial sums here, which is exactly the limit as n goes to infinity of what the partial sums are. So a 1 minus r to the n over 1 minus r. And now what we can do in this case is we can use our limit rules, specifically our geometric sequence limit rules, and get that this is equal to a minus the limit as n goes to infinity of Rn over 1 minus r. So I just brought the limit in to deal with the things that deal with the Rn. And then we know that if r, the absolute value of r, is less than 1, we know that this is going to, this limit here, as n goes to infinity of r sub n, is going to be equal to 0. That was just something we talked about in the very previous lecture. And if r is greater than 1, this limit n goes to infinity of Rn is going to diverge. It does not exist. Does not exist. And so what this means in terms of our series now, instead of in terms of our sequence, that if absolute value of R less than 1, then the sum from k equals 0 to infinity of a r to the k is going to be a over 1 minus r. Because this limit right here is going to disappear to 0 as n gets really, really big. Now, if the absolute value of r is greater than 1, and actually in this case we have r equals -1 as well. We know that this limit isn't going to, this limit does not exist as well. So if r is greater than 1, r equals -1, k equals 0 to infinity, a or k does not exist. It diverges. Does not exist. So the only case we have left, right, is this pesky case where r equals 1, but this turns out to not be too bad to deal with. So if r equals 1, well, our partial sum where we add up the first n elements is just going to be a plus a plus a plus a plus a. So the partial sum is just going to be n times a, right? Because I'm looking at this infinite series from k equals 0 to infinity of a now. Well, this is going to keep growing bigger and bigger and bigger, right? As I keep plugging in larger and larger n values, this is going to get bigger and bigger and bigger, and so this is going to diverge. And so we're actually left with the case where if my absolute value sign is going to be greater than or equal to 1, my infinite series will not exist. It's going to diverge. Okay, so these are what are called the geometric sums, and it's a very nice instance because we know exactly what my series is going to be equal to. Okay, so let's just go through some examples right now. The first example we're going to go through is the sum from k equals 0 to infinity of 4 times 7 over 9 to the k. Okay. And we'd like to compare this to sum from k equals 0 to infinity of a times r to the k. Well, if we match what we see on the left-hand side over here with what we see on the right-hand side, we're going to see that we have an a as 4 and an r as 7/9. Since we know that the absolute value of r is less than 1, right, it's 7/9, we know that this integral is going to converge. And we actually know explicitly what this, this series is going to converge to. So specifically, right, this is going to be equal to a over 1 minus r, which is 4 over 1 minus 7/9, which, if you simplify that out, is going to leave you with an 18. Okay, great. This is excellent, right? We took an infinite series, and we were very easily able to tell that it converges and that it converges to a value of 18. So as you keep summing more and more terms in this series, we're going to get closer and closer to this value of 18 right here. Let's go through another example of this. We'll go through a couple more examples where it might be a bit more difficult kind of to see what's happening. So the next example we're going to go through is going to be, we'd like to determine what 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... all the way out to infinity. So what we need to do in this case is we need to rewrite this in terms of our infinite series, hopefully rewrite it in terms of a geometric series. And then we will be able to use our values for our geometric series to actually figure out what this is going to be equal to. Now, the reason we're looking specifically at this example, which is very interesting, is something called Aesop's fable. So, the idea is that you are running a race, or I think he phrased it as a turtle running a race. He was an ancient Greek. And he says, okay, well, the first thing you have to do is you have to run the first half of the race. You do that, okay, takes some amount of time. And then the next thing you have to do is you have to run the next half of what you've run already. So we've run one half. And then we have to do this again, right? We have to run half of what we have left, which is going to be a quarter. So we have to run this next quarter. And then after that, right, we have to still make it halfway between where we are and the finish line. And so we have to run an eighth, and then a 16th, and then a 32nd, and so on and so forth, right? So the idea behind this, and it's just kind of a way to think about infinity and how our ideas of infinity might not always be right, is how can you ever possibly reach the end, right? We have to take this infinite number of steps, right? We have to take, we have to get halfway, and then we have to get halfway of halfway, and so on and so forth. It's very similar actually to this idea when we were dealing with these improper integrals of things with infinite width but still finite area, right? Infinity is really strange, and a lot of ideas that we might have of it aren't necessarily well formulated. Okay. But we're just interested in what this sum is in this class. We're not a philosophy class. You can kind of see from this picture, and a good guess for this is going to be it's actually going to sum up to 1, right? We are going to run all the way along this line right here in order to get to the end. So we hope that this is going to be equal to 1. Well, one way you could write this sum is the sum from k equals 1 to infinity of 1/2 to the k, right? What this does in this case is it is starting at 1/2, so k equals 1, k equals 2, k equals 3, k equals 4, so on and so forth. The problem with this, however, is that I have a k equals 1 here instead of a k equals 0. So this does not directly fall into our definition of this geometric series. However, there is a very easy conversion that we can do in order to get it back into this form where we have our bottom value at 0. So in particular, whenever we have an infinite series, our first term right here is always going to be what our a value is. So the first term is going to be our a value, right? It's going to be a times r to the 0, which is going to just be a. And then if we divide, can't spell today, divide terms, this is going to give me my r value, right? 1/2 divided by 1/4, or sorry, 1/4 divided by 1/2 will give me 1/2. 1/8 divided by 1/4 will give me 1/2, so on and so forth. So I can see from this sequence right here, my a value is going to be 1/2, and my distance between these two terms is going to be 1/2. I'm multiplying by 1/2 each time to get my next sequence. So instead of writing it, starting at a k value of 1, we can start at a k value of 0 to infinity of 1/2 times 1/2 to the k. And this makes sense, right? When I plug in k equals 0, I have 1/2. K equals 1 gives me 1/4. K equals 2 gives me 1/8, so on and so forth. So this is going to be the general technique that we're going to use to convert when we have something that's not starting at 0. But now we can actually solve this, right? We have an a as 1/2, r as 1/2, And so we get that this is equal to 1/2 over 1 minus 1/2, or 1/2 over 1/2, which is equal to 1, which is exactly what we want, right? This is the picture we drew right here is going to show us that this is the right answer. And we did this using our knowledge of geometric series. Okay. So as a quick example of something that diverges, k equals 0 to infinity of 1 over 14 times, just go with 1.001 to the k. Since this 1.001 is bigger than 1, we know that this is going to diverge. Okay, excellent. So let's go through one more quick example where we don't have a starting value of 0 now, we have a starting value of some other number. So let's deal with the sum from k equals 2 to infinity of 1 over 3 to the k. Or no, sorry, that was the wrong example. 3 times negative 3/4 to the k. Okay, there we go. So this almost looks like an infinite geometric series, right? We have this 3 here, which would be our a value, this negative 3/4, which is going to be our r value. The only problem that we have is that we are starting at k equals 2 instead of starting at our k equals 0. So similarly to before, let's write out the first couple of terms of the sequence, and we're actually going to be able to get to see that this is going to be equal to a geometric series. So a lot of times if you have something that looks really close to geometric series, but doesn't quite go into this form, a lot of times it's very helpful to write out the first terms of the sequence, and then we can rewrite the sum in terms of our infinite, or in terms of our geometric series. So this is going to be equal to 3 times negative 3/4 squared plus 3 times negative 3/4 cubed plus 3 times negative 3/4 to the 4th. So we can see between subsequent terms we are multiplying by a negative 3/4. And so this means that we do actually have a geometric series in this case. But now instead of having a starting a value of 3, my a is actually going to be equal to the first term in my sequence, right? This 3 times negative 3/4 squared, or 3 times 9 over 16. And what this also means, right, I can see that I'm multiplying by negative 3/4 every time, so r is a negative 3/4. Great, so we know that this series is going to converge. My absolute value of r is less than 1, so it's going to converge. And we can rewrite this as the sum from k equals 0 to infinity of 3 times negative 3/4 squared. And actually, let's just 27 over 16, which is what this a is, times negative 3/4 to the k. We can now plug in our values and get that this is going to be 27 over 16 over 1 minus a negative 3/4. You simplify, do all of the math, and we get this as 27 over 28. So as we keep adding up terms in this sequence right here, we're going to get closer and closer and closer to 27 over 8. And then as we take this limit, as we go to infinity here, we'll get this 27 over 8. That is what this number means. Okay. So we can use these geometric series in a lot more cases than just this one, and we're going to do this in a very similar way to when we were dealing with these sequences. So in particular, we're going to have a set of rules for how we can split up different series that we're interested in. And then if we have something that looks remotely like we might be able to use infinite series on it, we can normally split it up into a way that we should be able to. So the set of rules that we have, oh, that's the wrong picture. There we go, is going to be this properties of convergent series from the textbook, so theorem 10.8. The basic highlights of this are going to be, the first one is if you have a constant and you know your series converge, you multiply all the terms in the series by that constant, it's actually just going to be C times A. So it's similar to integration where you can pull constants out as long as we know that our series converges. So as long as we know we get some number as we take this series. Okay. So if it does diverge in that case, well, multiplying by a constant won't change anything unless we multiply by 0. Right? So if we multiply all of the terms by 0, we're just adding up 0 an infinite number of times. And so certainly that series will converge to 0. But in the case where we're multiplying by a non-zero constant, that's not going to change anything. It's still going to diverge, which is what's happening in this step 2. The third one is, again, very similar to integration. There's a lot of connections between integration and series, which is why it's covered in a calculus course. But we can pull out addition. So if we know that both of our series converges, we can split it up, so we're just looking at the sum of the first one and the sum of the second one. Okay. The fourth rule says it only takes one of the two sequences added together in order for the entire sequence to diverge. So if one diverges, that means adding anything that converges to it will keep it diverging. Note that we don't have a rule of where the two sequences diverge, and that's because there isn't one. Sometimes if you add two divergent sequences together, still diverge, and sometimes it will converge. Okay. And then the final one, which is a bit more technical and not one we will use really a ton in this class, but what it basically says is that if you know that some sequence converges, well, then you can actually start at any place you want along this sequence. So the example is we start at k equals 1 and say that it converges. That means that if we start at some larger value, so we just like cut off the first 30,000 terms or whatever, this will still converge. Or in the case where the first one diverges, the second one will also diverge and vice versa. We will mostly be using the converges one, so when we add two things together, it still converges, and then pulling out constants as well will be helpful for this. Okay, so let's go through an example of when we can use this. So let's say we are interested in the sum from k equals 2 to infinity of 1 over 3 to the k minus 2 over 3 to the k plus 2. Well, this should look like a geometric series to you, right? We have this 1/3 to the k, right? Just rewriting this slightly. This is sum k equals 2 to infinity of 1/3 to the k minus 2 times 1/3 to the k plus 2, right? So in this case, we kind of have an a as 1. In this case, we kind of have an a as -2. So if we say that these are going to converge, and let's assume they do for a second, and we will actually show that they do, we can split this up into this sum from k equals 2 to infinity of 1/3 to the k, and then minus a 2, so we can pull out a constant, sum from k equals 2 to infinity of 1/3 to the k plus 2. And now all we need to do is we need to figure out what these two sums are. This sum and this sum. And this is going to tell us whether this integral is going to diverge or whether it's going to converge. And it ends up converging in this case. So again, as I said before, this should remind you slightly of a geometric series. But again, similar to this last problem we dealt with, we now have a k equals 2 on the bottom instead of a k equals 0. But we now have a technique for dealing with this. So in this first case here, this sum is going to be 1/3 squared plus 1/3 cubed plus 1/3 to the fourth, so on and so forth. So going back to what we were talking about before, we know our first term will always be our a value, so we have an a as 1/3 squared or 1/9. And between subsequent terms, we are multiplying by 1/3, which means our r is going to be 1/3. So this is actually equal to the sum from k equals 0 to infinity of 1/9 times 1/3 to the k. 1/3 is definitely less than 1. It has an absolute value of less than 1. So this integral is going to converge, and we know what it converges to. Specifically, this is going to converge to 1/9 over 1 minus 1/3, which is 1/9 over 2/3, multiplying the top and bottom by 3/2. 3/2. Those are going to cancel, and I'm going to be left with a 1/6. Excellent. And for the second sum here, this green sum here, what I have now, something very similar, where I have now 1/3 to the fourth, right? So this is what happens when I plug in k equals 2. I get 2 plus 2 or 4, so 1/3 to the fourth, plus 1/3 to the fifth, plus 1/3 to the sixth, so on and so forth. And so my a then is this 1/3 to the fourth, which is going to be a 1 over 243, getting into kind of gross numbers, and my r is going to still be 1/3. Right, the reason my r is still 1/3 is that between each subsequent term, I'm still multiplying by 1/3. So even though I start at a much larger value, I'm going to get this r as 1/3 still. And so I can plug everything in and say this is k 0 to infinity of 1/3, or 1 over 243 times 1/3 to the k. And I can use my a over 1 minus r to solve what this is going to be. The math is going to get pretty nasty, so I don't want to do that in this case. Actually, yeah, no, don't want to do that in this case. And then what we can do is we can take the first sum here, where I do actually know what it's going to be. So it's this 1/6 I have here. And then I can subtract 2 from this green sum here. Whatever this is going to be, let's just call it some number x minus 2 times x, and this is going to give me my final answer. So this technique allows us to deal with different series, which might have multiple different geometric series in them, where they are expressed mostly by addition. One important thing to note, again, draw similarities back to integrals, is that there is no rule in this list about multiplication of two series that depend on k. Right, so if we have a constant, we can pull it out as long as the series converges, but there is no real rule for the series of ak times bk. This will, there's no good rule for it. It's like integration where there's no product rule. There's many different techniques that you might have to use in order to. Okay, so the final thing that we are going to talk about today in this section is going to be what are called telescoping series. So So telescoping series are basically series where a lot of the terms will cancel out. So we'll have, say, plus a 1/2, then minus a 1/2, so on and so forth. So the partial sums are going to be particularly easy to calculate. So let me give just kind of a very easy example at first, and then we'll talk about the more general technique we'll use to determine telescoping series. So let's look at the series from k equals 1 to infinity of cosine of k minus, 1 over k. 1 over k minus cosine of 1 over k plus 1. So if we write out the partial sums, right, call it S sub n, this is going to be cosine of 1 minus cosine of 1/2, right? This is what happens when we plug in 1, plus cosine of 1/2 minus cosine of 1/3. This is what happens when we plug in 2, plus cosine of 1/3 minus cosine of 1/4, and all the way down to cosine of 1 over n minus cosine of 1 over n plus 1. Now, the important thing to note here, though, is that we have this negative cosine of 1/2 and a positive cosine of 1/2. So those are going to go away. Negative cosine of 1/3, positive cosine of 1/3, so on and so forth. So we actually get that our partial sums are going to be cosine of 1 minus cosine of 1 over n plus 1. And this is why it's called telescoping, right? You can kind of imagine it as taking one of those telescopes that you can expand out and just collapsing it down into these two terms instead of all of the other terms that we had. But this allows for very easy calculation of what the limit is. So the limit as n goes to infinity of these partial sums, so cosine of 1 minus cosine of 1 over n plus 1. The cosine of 1 over n plus 1 is going to go to a 0, right? So we have cosine of 1 minus cosine of 0. We have 1 over some really, really big number, which is cosine of 1 minus 1, whatever that's going to be. I think the book says this is approximately negative 0.46 as our final answer. So the way we will most often see telescoping series in this course are either in this case where it's very obvious that you have an addition and then you have a subtraction right there, or it's going to be in the case of rational functions, right? So rational functions, again, are going to be polynomials or polynomials over polynomials, and we're going to look for partial fraction decomposition. And the reason we do this is we would like to get it in this form of something minus something else, and these are going to cancel. And partial fraction decomposition is going to give us a form that we are able to deal with. So in general, if you see either subtraction in your sum or you see some rational function, a thought that should cross your mind, and it won't always work, but one that should cross your mind is telescoping series. So let's deal now with an example where we do have these rational functions. So let's take the sum from k equals 2 to infinity of 1 over k minus 2, k minus 1. And we would like to know what this is equal to. Okay. Well, as I said before, we'd like to do a partial fraction decomposition on this. So 1 over k minus 2, k minus 1. This is just going to be equal to a over k minus 2 plus b over k minus 1. multiplying each side by this k minus 2 times a k minus 1, we're going to get that 1 is equal to a times k minus 2 plus b times k minus 1. Now I can use my techniques I used for partial fraction decomposition. Let's just say plug in k equals 2. And this is going to give me a b times 2 minus 1, or 1. So 1 is equal to b. Similarly, if I plug in a k equals 1, this is going to get rid of my b term. And I'm left with an a times a negative 1 equals 1. So 1 minus 2 is a negative 1. And this means a equals negative 1. So simplifying this sum, right, we get this is going to be 1 over k minus 1 minus 1 over k minus 2. And so because after we do the partial fraction decomposition right here, we are left with this subtraction, and we kind of get that one term might cancel with the next one because the bottoms are so close to each other. It's a good idea to at least write out the series and see that if you can use telescoping series techniques on it. So if I plug in, I start now at k equals 2 instead of, oh sorry, that should be at k equals 3 because otherwise I'm dividing by 0 the first time. K equals 3. What I can see then is that I now have this sum from k equals 3 to infinity, 1 over k minus 1 minus 1 over k minus 2. So k equals 3 is going to be a 1/2 minus a 1, right? So 3 minus 2 is 1. K equals 4. So this is my partial sum at n, is going to give me a plus 1/3 minus a 1/2. Then I have plus 1/4 minus 1/3, and so on and so forth until I actually get this plus 1 over n minus 1 minus 1 over n minus 2. And as we saw in the previous case, right, the 1/2s are going to cancel, the 1/3s are going to cancel, all the way down until I am eventually left with this negative 1, oops, sorry, I did that last part wrong. So we have plus 1 over n minus 1 minus 1 over n minus 2. And this is the one that's going to cancel. So I always go down and to the right first. So I have a minus 1 plus 1 over n minus 1. Okay. And so as I take the limit as n goes to infinity of these partial sums, so negative 1 plus 1 over n minus 1, this is going to be equal to negative 1. And what this means then is that my sum is actually going to be equal to a negative 1. And I just realized that I did make a mistake here with my positive and negative, so let's go back and fix that really quick. So I actually have these a's and b's flipped. So this should be a b, and this should be an a. And the reason I made this mistake is when I multiply the left and the right side by k minus 2 times k minus 1, right, I will get a b times k minus 1 because the k minus 2's will cancel. And so instead, I actually have a negative 1 over k minus 1 and a positive 1 over k minus 2. So negative and positive. What that does here is it changes all of these negative signs around and all of these positive signs around. So now all of these terms are my negatives and all of these are my positives. All right, just as an insight of why I caught this mistake, if I look at this sum right here, I am adding up a bunch of positive things, right? It's always 1 over a positive number. So I expect if I add up a bunch of positive things to get a positive number out in my answer. So this negative 1 I have here does not make sense for that reason of I'm getting a negative number. Okay. So the cancellations will still occur in this case, right? Negative 1/2 plus 1/2 negative 1/3 plus 1/3 all the way down. But now I'm eventually left with my partial sum of n is going to be 1 minus 1 over n minus 1. Again, taking limits of these partial sums of s sub n is going to give me 1. And so because this limit exists, the infinite series is going to converge, and I have the sum from k equals 3 to infinity of 1 over k minus 2, k minus 1 is going to be equal to 1. Great, so this is another way for dealing with infinite series. And in the next sections, we'll talk about a couple of more tests to tell whether a series converges or diverges if it doesn't fall into one of these two fairly niche